are the three derivatives? We will eat, sleep, snore, derivatives until about January or February. And then we will do antiderivatives. It starts out with nothing new, as you will see. All right? The definition of a derivative is as such. That look familiar? That should.
Yes.
It's the same thing as an instantaneous rate, isn't it? It's the limit as h approaches 0 of the fraction f of x plus h minus f of x all over h. With one difference. You see this little thing here? I will explain this in a moment. Yeah, I still want you to write it. Okay? Because my derivative is this thing right here. So in case you're going to guess, this is notation for a derivative. All right? Yes, it does have to have apostrophe. Because if it didn't have apostrophe, wouldn't it, wouldn't it just be the original function? F of x? How do I know the difference between the original function and the derivative? Right there. It's a good question. Now, there is an alternative definition which you hardly ever use. I'm going to throw it out there at you. And this is really the derivative at a point. But we can really still use this and then plug in that point or whatever. But every once in a while, maybe you see something like this. Okay, where x is a. I have a derivative right here where x is a. Well, the derivative of the function at a is the limit as x approaches a of f of x minus f of a all over x. This is kind of like, you know, y2 minus y1 over x2 minus x1 kind of deal. But we hardly ever do that. And when I show you the shortcuts to derivatives, you're hardly ever going to do this ever again, ever. In the history of math, you will never do this unless you teach it. Once I show you the other way, which is a million times shorter and easier, yeah, and you're going to want to throw notebooks, pens, sharp objects, spears, javelins, water bottles, the hard ones. You'll never use this fraction ever again. All right? So, let's talk about notation. Okay? When we have an equation, all right, we can say y equals, I don't know, x cubed minus 2x squared plus 7. Whatever our equation is, it could be y equals. But if we want the derivative of y, we just call this y prime. That's how we say it. We say y prime. All right? So if I'm up here and I'm like y prime, I mean the derivative of y. Simple. You've seen this next one was in the previous slide. And if I'm given a function f of x, and I want the derivative of f of x, I just say f prime of x. Okay? F prime of x. And there's two more in the book that I'm not too crazy about. I don't say them this way. That's the derivative of your function with respect to x. Okay? To me, it seems like this should be this one. The derivative of your function with respect to x. Maybe the derivative of y with respect to x. But I just say it's dy dx. I'll say dy dx. You can literally say dy dx. Okay? I'll say find the derivative of y. You can write it like this. You can write it like this. I mean, there's several ways. This last one is the derivative of f at x. Okay, that's the derivative of f of x as well. It's all just the same thing. All right? I'm not going to test you on these, but you should know what this notation means. Especially the first two. The first three, really. They all mean the same thing. You'll get very familiar with them. We'll see them all over the place. Oh, you okay there? In the future, all will become clear. It will. It will. And that's the moment where you guys get so upset. It's crazy. I can't wait. All right. Example. Find the derivative of f of x is x cubed. Okay, find the derivative of the function f of x, which is equal to x cubed. We are still going to use, okay, the derivative of our function f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, this is cubed. This is no longer squared. I still do the same thing. I still plug in. It's the limits as h approaches 0 of x plus h cubed, because I got to throw that into here, don't I? X plus h. Minus my original function, which is just x cubed, all over h. Now, I'm going to tell you a little story, children. You know how we can quickly FOIL x plus h squared? We can quickly FOIL x plus h cubed. Does anyone know that quickly or no? All right. Do you want to know how I learned it? In college, when I was taking a math class, and x plus h cubed would come up, and I was in a different, you don't have to write this down if you don't want to. And if I had x plus h cubed, well, I know that's x plus h times x plus h times x plus h. I know these two, we're good at this. It's x squared plus 2xh plus h squared. And I still have to do this. And while I'm doing this work and FOILing this out, kids are ripping it off in college. I'm like, how the? And I'm like, I know I'm smarter than they are. I know a million times smarter. There's something I'm missing. Something that I was not taught, or if I was taught, I didn't pay attention to it. Do any of you guys remember Pascal's triangle?
Sort of. It's a triangle.
It is. Very good. It's triangle. Actually, that throws most people off. It's a three-sided figure, but it's not a triangle.
Yeah, because you're here.
Stop it! It's a triangle. It's called Pascal's triangle. It's triangle. Shame on you. Shame on you. Okay, it starts with a 1. Then it's a yes. Hey, look, you don't have to memorize this. You can do it this way. You can absolutely do it this way. And I'm just saying, you a little longer. That's fine. We don't grade you on the time it takes you to do a test. Okay? Then we have a 1 and a 1. There's always ones on the outside. Then a 1, and then I got to add 1 plus 1. 2, 1. Then a 1, and I got 1 plus 2 is 3. 1 plus 2 is 3. And then a 1 on the outside. Then 1, what goes here?
4.
4, what goes here? What goes here?
4.
1, and a 1. We'll do one more.
5,
5,
10,
10.
10, 5, 1.
Okay, do you know what these represent?
1, 6.
And until I actually look this up, I'm like, aha! I knew they weren't smarter than me. I knew I missed something. If anything is to the power of 0, it just, isn't it equal to 1?
Yes.
Okay, if anything is to the first power, that's like a straight line, right? Like x plus 7.
Yeah.
You have 1 and 1. If anything is squared, these are the coefficients, 1, 2, 1. Isn't this squared? 1, 2, 1. Aren't those your coefficients? Yeah, you see? I'm cubing this, aren't I?
Yeah.
I know it's got to start 1, 3, 3, 1. I know those have to be the coefficients. So what goes with them? I take each term, x, h, x, h, x, h, x, h. Does some of you remember this? And then the x starts 3, and it goes down. 2, 1, 0. Then the h just goes the opposite way. I can start in the back of the 3 and go 3, 2, or I can start at 0 and go 1, 2, 3. Either way, they should add to 3, because the exponent is 3, isn't it? These two should add to 3, 3 and 0. 2 plus 1. 1 plus 2. 0. So when I do this quickly, anything with 0 goes away. I have x cubed plus 3x squared h plus 3x to the first h squared. This goes away, boom. Plus h cubed. Now, here's a $1 million question, children. What if it wasn't just x and h? What if I had a 2 here? Guess what? I put 2x and I cube it. See what I'm saying? Whatever that term is what I put here. Do you see what I'm saying? Let's do another cube. Okay? Let's do another cube. Let's do 2x plus 3h cubed. I know it's 1, 3, 3, 1. I'm going to take each term. 2x, 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 2x. I should really put that in parentheses. And then 3h, right? 3h, 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 3h. In my exponents, aren't they? 3 for the x, 2 for the x, 1, 0. And then I'll start at the back. 3, 2, 1, 0. Anything with a 0? Bonk. I got to cube the 2 and the x. Okay, 3. 2x squared, well, that's 4x squared. 3h. 3 times 3 is 9 times 4.
Wait, you times it by 2?
I squared my 2x.
Oh, okay, okay.
2x times 2x is 4x squared. So I get 36, I have an x squared, and I have an h. Okay, this is just 2x. Well, if I square 3h, right, I got to square the 3 and the h. What is 2 times 3
6,
times 9?
6,
6 times 9 is, you need to hold up your fingers. 54 x h squared. And the 0 goes away, boom, plus 3h cubed. 47, 52, 3, 4, 54! God, I'm good at math. Okay, so as I do this, that's just a shortcut. I mean, Pascal's triangle. It's nice. So let's go back here. And because if I just did this without telling you how I got it, you're like, that's not how. I don't see hands all over the place. So it's the limits. As h approaches 0, I'm going to use my shortcut here. That's x cubed plus 3x squared h to the first, plus 3x to the first h squared, plus h cubed. I just expanded this right here using that Pascal's triangle. Well, I'm not done, but yeah. But don't forget, minus x cubed. I have to subtract x cubed. And I'm going to do that in a different color. Why am I going to do that in a different color? All over h. Because you should recognize that whatever is in the back here should cancel with something in the front, shouldn't it? And everything left has to have an h so I can cancel it. It's the same thing, same thing. Nothing is different. This one h cancels with this one h, cancels with one of these, becomes a 1. This one of these and becomes a 2. So now, I have the limits as h approaches 0 of 3x squared plus 3xh plus h squared. Miss Donovan, looking at this, what's the derivative going to be? Sasha, you can do that in her head? You're going to be able to do it that quickly in her head, too. It's 3x squared. But let's check to see if that's right. Anything that's an h goes to 0. Here's an h, 0. Here's an h, 0. You're going to be able to do it that fast as well. And when you do, you guys are going to be so pissed. I'm going to bring in a video camera that time. And I'm going to show you guys your faces on the board. It'll be like you looking at each other. You'll get my view.
That's one right now.
17. That's right. All right. So, yeah. So we still use our fraction here. The limit is h approaches 0. The difference quotient, is that what it's called? I don't even know what it's called. I just know how to use it. Terrible. Nothing. The fraction, I believe it's called a difference quotient. So, not bad. It was a little bit more work because that was cubed. All right. Now, let's take a look at the next one. Pascal's triangle. Beautiful. Now, let's take a look at this one here. They want to know right at x equals a. Now, if this was simple, I can still use my limit as h equal to 0, whatever, and plug a in for x at the end. I could do that. But sometimes, right at a, and that's the limit as x approaches a. Okay, sorry, I forgot to do that. All right, we're going to use that second one. You will hardly ever have to use it. We'll always have to use that first one. The second one you hardly have to use, but I want to show you an example of it. Now, I'm going to take the function f of x, which is given to me right here. So that's the limit as x approaches a of the square root of x minus the function with a in it. So if I put an a here, don't I have to put an a here? Radical a all over x minus a. Now, you may have forgotten this, but anytime I want to get rid of radicals, so I multiply by something called the, begins to C conjugate.
Oh, conjugate.
Yes, conjugate. Yeah. So that's the same thing. Radical x, radical a, except you just change the sign in the middle. You don't negate both terms, just change the sign. What I do to the top of a fraction,
I do to the bottom.
I have to to the bottom, and watch what happens, children.
It
Oh, next slide, Nick, let's see. Equals the limit as x approaches a. Okay, I'm going to FOIL this. X, radical x times radical x. 1x. Radical x times radical x will be radical x squared. The radical and the square cancel. Is x. Okay? Radical x times a, radical x times radical a is plus radical xa. They're all under the radical. Negative radical a times radical x minus radical xa. That's nice little cancel. Negative times a positive is negative. Radical a times radical a, it's a. All over, and I'm going to leave the bottom the way it is. X minus a times the square root of x plus the square root of a. So, what do we got here? These cancel, and on top I'm just left with what?
X plus.
X, well, plus a negative a, that's like x minus a, right?
I'm like, what is that?
And this x minus a can cancel with this x minus a. So I have the limit as x approaches a of 1 over radical x plus radical a. Doesn't my x turn into an a?
Yep.
Oh, it does. Oh, it does. So I've got 1 over radical a plus radical a. So that's 1 over what? What happens if I have 1 radical a plus 1 radical a?
2 radicals.
There you go. One-sided derivatives, just like limits, you have one-sided derivatives, but they're very. Oh man. The derivative of this first one. So we're going to take derivative of both these. You ready? This first one is actually going to be 2x. What's down and what's the derivative of the bottom one going to be? Let's see if we're right. Yeah, wait till you guys learn it. I can't wait. Left-hand derivatives. That means all the values smaller than x, correct? So I'd use the top or bottom expression. I'd use the top one. This is left. Left of 0 is this one. Okay? Right of 0 is this one. So when I ask this for the left side, I'm still going to do the limit as h approaches 0 of x squared. Well, actually, I want to take the derivative of x squared. That means the limit is of f of x minus h plus f of x all over h for this function right here. You want me to pause this? You guys try it. I'll do it up here so you get the same answer. It's plus h. I had a plus. I don't know what you're talking about. It's called movie magic right there. I did.
Will it still be plus f of x?
No. It's minus f of x.
What the hell? It is?
Yeah, that's how I wrote it. I'm pausing the video and changing it and recording it again so it looks like it was right magically. These are just what I'm saying I'm going to end up with when I do this. The sound saying this is what you're going to end up when you do that because we can do it quickly and we're going to teach you that way.
-2x. Stop.
Okay, so let's do this here. That's x plus h squared minus x squared all over h where h approaches 0, right? Who can tell me what's x plus h squared? This is the easy one.
X squared plus 2x.
Very good. Minus x squared all over h. Very good. And don't our x squareds cancel? They should. And everything left should have an h in it. Bang. Bang. So we've got 2x plus h, where h approaches 0, remember? It is 2x, just like I said. All right. Whew. Thanks, you can come up here and do the right-hand one. 2x. Adrian's got, oh, Adrian already had it. So look it. The derivative of the left side was indeed 2x. Let's see if Adrian can do the derivative of the right side, which the function itself given is 2x. It's not that we're going to take the derivative of the derivative. It happens to be that they're both related that way. Okay? That's a good question. Yeah. Perfect. He took x plus h and put it in for x. So it's 2 times x plus h minus 2x all over h. Perfect. And what does the top turn into? You got to do what? Yes. So go ahead. 2x, no, 2h minus 2x all over h. Now, yeah, there we go. I like changing the colors, like a teacher does. So they turn into 2 blue x's. Yeah, and what are you left with? 2. Equals, go ahead, right equals 2. Go ahead, equals 2. Now, $1 million question here, Adrian. 2. That's as h approaches 0, right?
So it's x.
Wait, get back. Now, where's the h to throw the 0? There is no h, so it's just 2.
Yeah.
I don't have to throw 0. Now, look it. These are at points. I could have done f of x minus f of a all over x minus a at a point, and it would have been 0. Would have been my a. But that's, to do this, look how easy this was. This was good, people. This was good. Are they the same? Is 2x the same as 2? At 0? When x is 0, what's one thing we need to do here? X equals 0, so shouldn't I throw a 0 in there? So when I evaluate that, what's 2 times 0? The actual derivative is going to be 0. I can find the derivative using 2x for any value of x. They gave us a value of 0 for x, didn't they?
Yes.
Okay, and just like there's no h to throw in a 0, there's no x to throw in a 0, is there?
No.
So this actually is 2. 2 does not equal 0. So guess what that means? That for the left side and the right side, it's not the same?
It does not exist.
There is no derivative at 0. Because when the derivative from the right side and the derivative from the left side are not the same. the function does not have a derivative at x equals 0. So you know what we say when it has no derivative? That the function is not differentiable. You're gonna say there's no derivative. But if you see the words not differentiable, you should be like, oh, that means no derivative.
I'm not going to give you like, yeah, my math teacher told me that English word.
Okay.
Wait.
How about that dude? Someone said wait. All right. And we only have one more thing left to do here. And then there's homework and, you know, all the proof that comes with it. Thank you. Thank you. I tried. Now, we're going to take a look at the graph of an equation, a graph of some function, and then we're going to graph the slope of that function. Who can tell me what really is derivative? The derivative really represents what? When I did the change in speed, the average speed of a rock falling, remember that from like 0 seconds? It's what? Okay, no, you might be, I don't know what you're doing, you might be. There's instantaneous rate of change, and there's the average rate of change. How do we put the average? Instantaneous was that f of x plus. Well, what about the average rate of change? What did I do? y2 minus y1 and what is that really? y2 minus y1 over x2. Slope. Instantaneous is the slope at that point. All right. Average is the slope between 2 points. Instantaneous is the slope at a point. So if derivative is the same thing, what do you think derivative is? It's the same thing. Derivative is really the slope at a point. So if I go back here, what's the derivative of x squared? Is 2x. So if I pick, like, well, what about when x is 1 at x squared parabola? What's the slope? I throw 1 in for my x. 2. It's 2. What about at 3 in this parabola x squared? What's the slope?
6.
6. 2 times 3. That's how you figure out the slope. It's different from the value of x at that point. So when I go here, let's take a look at this. If I look at this point A. This is my original function, okay? Point A is telling you, it draws a tangent line. It's telling you that's a slope of 4. That means A should be at 4 when you graph this, what the graph of the derivative would look like, right? Because the derivative is 4. When x is 0, the derivative is 4. So at 0, 4 is the point. So let's look at point B. When x is 1, what's the slope at B? 1. So I go to 1. Yeah, that's kind of way out. Right there. The slope is 1. You see what I'm saying? We're just plotting. The derivative becomes the y value when I graph. For example, x equals 1. The slope is 1, isn't it? This is where that's going at 1, 1 right here. Let's look at when x is 3. I'm looking at this dot. What's the slope? So when x is 3, the slope is -1. So I'm putting it 3, -1 on this graph. I go to 3, I go to -1. You see that? Bop. Bop, bop. Ooh, we missed one. What about at 2? What's the slope? 0. So it's at 2, 0. So I go to 2, 0. Whenever the slope is 0, what on the graph, what's it going to be? It's going to be an x-intercept, isn't it? Mind blown. So what about at 5? When x is 5, what's my slope? So that's at 5, -1 on the graph, the derivative. 5, -1, bam. And what about at 6? What's the slope? And when it's 0, isn't that an x-intercept? So if I were to connect those dots I just put, This is the graph of the derivative, and the derivative is also known as the slope. I just graphed what the slope of this is at every point. Crazy. The derivative really just replaces the y value. The derivative replaces the y value. Don't